Hi, how you doing? Um, this is going to be my third episode, and I know I promised you guys to talk about relativity right now, but here's the problem. I almost don't have time for these videos, so I've been a long time for me trying to make these videos possible, and always put it for later. So I just said, you know what? Even if I'm not ready for it, I'm just gonna jump in, and it's like jumping in the pool without swimsuit on. I just jump with whatever I have, and then just start sorting things out later. Um, so I wanted to first start just like in my theory that I created 22 years ago. I placed it online. I stayed like that for 21 years. And last year it was taken off because of some problem with the server. But anyways, I decided to put it on YouTube, and I wanted to do that, and I keep putting it for later. And when I went in, I started getting excited, and I began telling you the end of the theory, because the end of the theory, I guess, it's more interesting. You know, the end of the theory, because I explain things that nobody has explained before, like why the universe is oval in shape, and why it's accelerating, and all that stuff. And all that stuff I have it inside my head. I haven't gone to my papers to really refresh. So I thought I finished with the ending, but I didn't, because there are still some questions. Like for example, I wanted to explain now, because later I forgot on the other video. But to the truth, I'm not done with the ending yet, and there's still some questions. So I want to finish with this video all that I need to say, finish the ending, and then go back to the beginning, which is relativity. The universe is connected, but not connected the way people say. You know, like a chain. No, it's kind of like a, well, it's not like Legos that you connect and disconnect. I mean, if you connect something, that means that you can disconnect it. But the universe is connected in a way that is one. It's like taking all the Legos and then taking a torch and just melting all the Legos all together until you have a nice patty on the floor, and you can pick it up, and it's all together. That's the universe. So the universe is one. Everything. Our minds tell us that's different, because we have learned. I mean, since we were fish, you know, we gather a sentient mind, and we have self-awareness. We became aware of territoriality, and what we need to dig over here. If it's a fish, you need to dig over here and put rocks over there. And this is one rock, and you put it over there. It's another rock, and you put it over there. So the mind starts dividing things, picking up things, and putting it over there, and putting territorial ground. So this is my place, you know, for me to live, and for me to have sex, and for me to breed. So we start making barriers, and we start, and we need to find out where we go. So we need to find out different, we need to have an awareness of space that we are, directions and stuff. I'm pretty sure that the direct in a fish mind, the direction part of the brain is more developed in our own, because we're mammals and we just walk, you know, in a solid state. Sometimes we go up and down, but a fish goes all over the place, so it needs to have a better sense of direction. So the thing is, we develop all this stuff of dividing and subtracting and making the divisions of the reality that we're in. So reality is a process of mind that is actually a perspective. It's a perspective of reality. It's not really what reality actually is. Reality is completely different. So the universe, we think like space and time and infinity and matter and antimatter and energy and a few other things I'm not going to get into, but we think of those things as being a part of each other, you know, connected but a part of each other, and they are not. Everything is one because it came from one. From the beginning, everything was one, and now it's, even though it doesn't look like it's one, it's still one. Everything is together, and I'm going to get into that but later after I finish this theory, and I'm probably going to call it the chef and the potato. That's what I'm going to call it. When you see the chef and the potato, that's what I'm going to talk about the oneness of the universe. Anyways, so because the universe is one, this theory fits from another perspective. So I wanted to talk about the why is it that when a dark collapse star, becomes a dark collapse star. Oh, by the way, the title of this thing is black holes don't exist, only dark collapse stars. That's because we need to change the name from black holes to dark collapse stars. Okay, in my views. Okay, because in my view, a dark collapse star is the beginning and the end. I mean, it's the creation of everything. That's where universe are born, and that's where universe die. That is what everything starts there. They are the starters of every universe within universe within universe. They are the starters of every universe, and they deserve more respect than just call them black holes. And before, we used to think that there were black holes and that you could get into them and go to some other universe, but that's not the case, because they are a compressed matter that has been compressed to its ultimate state, and it's spinning very fast. So that's why I say there are no such thing as black holes, only dark collapse stars, because that's exactly what they are, dark collapse stars. And the name should be changed. I mean, we change Pluto, which I believe is a planet, and we change it from not being a planet. And if we did that, how come we are not doing this? We know that they are not black holes anymore. We know that they are something else. Some scientists may not believe in what I'm talking about right here, but even that in that way, black holes are not black holes. Okay, so I just want to leave on that and start with the other question, because I haven't finished what I did the last time. I show you how the universe is accelerating, but one thing that many people might think is, okay, if a dark collapse star goes supernova and then it turns into time-space itself, how come that time-space doesn't actually dissolve in the other time space? I mean, why is it that time space, if it becomes time space, right, then it should attract the other time space of the universe, and the universe will the gravitational the collapse of time space that goes into the dark collapse star we have just been formed, and it's only time space with a tiny universe inside. If it's time space too, so why doesn't the time space on the outside, okay, of the dark collapse star just travels into the inside of the dark collapse star, thereby expanding that time space in there and just making it balanced again, and it probably turning it back into matter, because it will just expand again into the universe. So I don't know if you guys understood what I'm trying to say, but you will, hopefully you will, and if you don't, then just leave me comments. But the thing about it is, the reason for that is because this is an amazing thing. When a dark collapse star, okay, when a supernova turns into a dark collapse star, it is a curved time space. Okay, it's a curved time space, and because it's a curved time space, and not only that, the time space on the inside of the dark collapse star, okay, even though it's a curved time space, the time space on the inside of the dark collapse star is slower, okay, much slower than the time space on the outside of the dark collapse star. Okay, so everything that goes in there is slower. So even though I have an example here, hopefully my camera will be able to focus right. I don't think it will focus right. I think it will probably look like a porcupine, but those that are okay, this right here in white, the line in white, is a dark collapse star, and it's spinning very fast, so it's oval in shape, and this is the axis okay, and the universe is right in there, okay. Probably a very old universe, since you can actually see it with the naked eye, and it's probably it wouldn't probably look like that way. It would probably look very dim. But anyways, it's just an example. All right. So the universe, as you can see, it is oval in shape, but in a vertical manner, while the dark cloud star is vertical, is oval in shape in a horizontal manner. Okay. So what happened is, let me enlarge this. Something that I haven't seen anybody talk about. Okay. This over here, which is the edge of the dark cloud star, is what I would call a time wall. Now, nobody knows what time walls are right now. I googled it, and what I got was a bunch of clocks on a wall. But what a time wall is, if you search my last episode, I said that because it's curved time, it's a curved time space. Over here, time space is slower, as it reaches the outside. Okay, it gets faster and faster because time space expands as it reaches the outside. The time space goes faster and faster. But even the time space on the edge of the new universe, you know, inside the dark cloud star, all this space here is time and space. All this time and space over here, excuse me. Okay, all this time and space right here. From here is slow, from here is faster. But even the fastest time here. Okay, I think I need to do something here. There, now Siri won't bother me anymore. Okay. What? Oh wait, it's a series on my iPhone. Oh great. Let me just turn it up here. Okay. Sorry. Okay, so anyways, so here's the dark cloud star. Alright. Okay. And these are arrows. As you can see, they are arrows. These arrows are time space collapsing this way, and on the outside of the dark cloud star there's time space collapsing this way. So in other words, gravitational pull is this way on the outside of the dark cloud star, and the inside of the dark cloud star, gravitational pulls this way. Okay, how is that happening? Because the time space inside the dark cloud star is curved. Okay, it's curved. If you threw a light beam, okay, inside the dark cloud star, it will go around and around and around because the time space is curved. Okay, so anyways, but over here time space is slow, over here time space is faster, over here time outside the dark cloud star time space is really fast. So because time space over here is really fast, and over here in the dark cloud star, okay, the edge of the dark cloud star, time space is dilated. You have dilation, so naturally time space flows in, trying to balance the equation, trying to balance the fact that the slower time space here and longer and faster time here. It's trying to balance the time space, because time space always wants to balance itself out in time. So anyways, because of that, it's flowing in, attempting to widen, attempting to get the time space inside the dark cloud star to get wider, okay, wider. But because it is doing it all over the dark cloud star in a global manner, okay, so it is trying to expand the time space because it's dilated. It's trying to expand it by flowing into it, but it's flowing into it all over because it's a globe, okay. By flowing in all over, okay, what it actually does is keep it compressed, okay. So it keeps the time space compressed, the time space of the dark cloud star compressed, okay. And because the time space on the inside, time space on the inside of the dark cloud star is also curved, so it's pushing to the outside because time space is flowing this way because it's curved. It's flowing this way, trying to balance the over here, trying to balance and expand over here, expand the time space in here, okay, to make it equal. but because it's curved, it cannot do it. So it continues flowing to the edges, So because of that, you get two different time space flows. So one process of acceleration. Okay, time space flow is a process of acceleration. If you have seen before, gravity is a process of acceleration. Anyway, so you get a gravity flow going outward here because of the space that is distorted. You get a gravitational pull that goes outward towards the outside, which is why the universe is expanding and accelerating. Okay, and on the outside you get acceleration also, because the time space on the inside of the dark star is dilated, okay, ready to the outside. So you get a time space collapse, okay, on the outside, trying to take the dark star apart and balance it, but because it's doing it in a global manner, all it does is compress it even more. And what is compressing it, the outside time space, the inside time space of the dark collapsed star is pushing out. Okay, so you get two processes of acceleration: one inside the collapsed star, one inside the dark collapsed star, going outward, and the other one on the outside of the dark collapsed star, going inward. So what you actually get is a time wall. Okay, it's a time wall. It's a wall of time. I just wanted to say that, because that's the last part of what the dark collapsed star is. The other thing that I wanted to show you was a good way to find out how much time goes over here, how much time passes here. Okay, relative to how much time passes here would be like, let's say, well, over here in the universe, from here. Okay, I had a little bit of problem holding the iPad. Right over here, hope you guys can see it. Maybe like this. Okay. So in order to find the right amount of time dilation, okay, over here, that's happening here, relative to over here. Okay. Let's say. Oh, by the way, when I say if you throw a beam of light, it will go around and around. It's just a symbolism, just metaphorical, just to get you to know that time is dilated. I mean, if you throw a beam of light in a universe, it will probably just won't make it much, and it will end up, going towards the outside of the universe. But let's not talk about that. What I'm trying to say is that because the universe is curved, okay, if light could travel at a very fast speed within that universe, okay, it will travel around and around, okay, until it just dissipates because of gravitation. The relative time space is going outward, so it will go around, and then it would end up disappearing on the time walls. Okay. But anyways, I shouldn't have taken that. I just wanted to make a symbolism out of it, not make it real. It's just to say that time space is curved, so if you throw a beam of light, it will just go around. Okay. So anyways, in order to find out how much time dilation is here, be ready to the time expansion here, let's say if it was a second, if there was a second of time that a light beam will go from here to here in a second, then a beam of light over here will also, if they were both released at the same time, they will both end up being over here in a second, in 1 second, because time will be dilated. So there's a curve. So in order to find out how much time dilation there is, I took this little piece over here from the universe, this little piece, okay, which is what we are, this is exactly what we are actually measuring over here. So I took that little piece and I put it over here, how many times it will fit here, okay, and if it fit, I think about 17 times or something like that. So that would mean that for every second that goes over here, all right, 17 seconds will happen here, okay? because this time space over here is 1 second, and this time space over here, it takes the same amount, 1 second, to reach over here. However, because this over here is 17 times larger, okay, so that means that for every second that goes here, 17 seconds happens here, okay. For every second that goes here, 17 seconds happen here on the outside of the dark black star, the inside of the dark black star, okay. But on the edge, right? That's what I'm trying to say. So you may think that's not much of a time dilation, but imagine if every second that goes here, all right, 17 seconds goes someplace else. Imagine how many seconds that add up, you know, for every second, all right? Just do the math. It is a very hard time dilation, okay? So anyways, now that I explained that, hopefully I finish with the ending of my theory, theory of the universe. Well, not really the ending, because I need to explain the oneness of the universe. I need to do that, but first I'm going to go back to the beginning and teach you about relativity, okay? Because relativity is not what you are taught in school. I watched many videos about relativity, and including Carl Sagan's Cosmos, which was one of my favorites. That's where I got my passion for physics, with Carl Sagan's series Cosmos, and it was so fun to watch it. So anyways, yeah, what thing that I'm trying to say is relativity wasn't shown there that well, and it's not shown in any samples that well. But to tell the truth, when you really look at relativity in a deep sense, if you're standing still in outer space, or even here, but outer space is much better, right, because you get a better sense. If I'm standing still in outer space, okay, in a spacecraft in outer space, right, relative to some other object in space at infinity, okay, I will be traveling, okay, at infinity directions and at infinity speeds relative to some other object. An example is if there are many objects coming in many different directions and many different speeds around my spacecraft, okay, for every one of those objects that is passing by, I am the one going at exactly the opposite direction at exactly the same speed, and that is because we are standing still. No, another thing I would like to add, you might think, why in the world a universe is smaller than other universes, and then matter is smaller, and then things become smaller and smaller, okay? And it's the relativity of matter and space-time. Let me put it this way. When matter is made there, okay, it is shattered by the powerful collapse of the matter becoming time and space and heading towards the center, okay? If you know what I mean, just look up my my first episode. I'm going to put numbers on it. Anyways, when a dark black star is making itself, zipping matter into time and space all the way in, okay, and then it shatters in the center. Because it shatters in the smaller time space, the matter in there is going to be as small as relative to that time space. Let's just say that that the universe for some reason will shatter matter, okay? Will shatter nothingness. Will shatter nothingness, right? Let's say that instead of shattering nothingness in the center, it will shatter nothingness on the side over here, where time space will be larger, okay? Over here, if time space is shattered here, okay, matter will be larger than here, okay, because time space will be larger. So matter actually changes in in size, okay, because it's time-space. Matter is time and space. And if the time and space is large, so when you shatter that time and space as large, matter becomes it's larger. But if it's found in a smaller area, okay, where time and space is, okay, then the matter there, that when nothing is shattered, when I mean by nothing, I mean time and space. When nothingness gets shattered in the center, because it's the smallest time and space that there is, the matter there that develops is very tiny. At the same time, that's good, okay, because that means that the universe that's going to be born in there, it's going to be so small relative to the size of the whole entire time space, relative to the whole entire time space sphere, okay. It's going to be so small that it's going to give chance when it appears in that process of acceleration that's getting faster and faster while it's going out. It's going to give more chance for the universe to last, or well, since there's life, I believe there's life in every
Okay, just got a little bit dark in here because
you'll get much better chance for life to survive in that universe. Okay.